First section, the sun. So hopefully you've never looked at the sun directly with your eyes. This is a terrible idea, don't do it. However, if you have a telescope, and you set it up properly, or a pair of binoculars and you set them up properly, project the sun onto a piece of paper, this is something like this is what you'll see. So the only really standout feature on this picture, right, are these dark spots. These dark spots are sunspots, and they come and go, as we'll discuss in a minute. But this is really where our problems start in terms of space weather. And you can't really tell that, with the naked eye, with visible light, this looks like a fairly benign situation, and you wouldn't really think much was going on. The real breakthrough came when the first satellites carried UV images. So UV light from the sun doesn't reach the ground, it's absorbed by the upper atmosphere. So you have to go into space to take a UV picture of the sun. And when you do, and you take a video and you speed it up, this is what you see. So all these bright spots are sunspots, where magnetic field is coming out of the sun. So you can see these loops of magnetic field between these bright points. So sunspots are the footpoints of these very large loops of magnetic field. And this magnetic field is really dynamic. I mean, this is speeded up, so a day is only lasting a couple of seconds. But you can see that every day these tubes are moving around and changing and swapping positions. So it's the magnetic field of the sun, which pokes out through the surface in sunspots, that's really causing this dynamic situation to evolve. And you can see it in UV light because these magnetic fields are trapping the plasma of the sun and heating it up. So these patches are bright because they're dense and they're hot compared to the rest of the sun. So okay, we think sunspots are the most important, or are a very important part of this solar activity. So let's take a quick look at sunspots in detail. So sunspots are dark. They're dark because they're colder than the rest of the surface of the sun. They're still a few thousand degrees Kelvin. They're not cold, but they're just colder than the rest of the sun. And the reason for that is the strong magnetic field. So the magnetic field there is acting to contain the plasma and keep it cold. And sunspots always come in groups. So this whole group here is called an active region. An active region is a group of sunspots that are sort of magnetically linked together. The center of the sunspot is called the umbra, and the surrounding darker area is called the penumbra. And these are very, very dynamic systems that change on a day-to-day basis. Although individual sunspots can last for many weeks or even months if they're very intense. We've known about sunspots basically ever since the telescope was invented. So one of the first things that Galileo did was look at the sun, and he saw dark spots and started measuring them. And in fact, before the telescope was invented, there were reports of sunspots. So you can see them. Again, don't look at the sun with your eye, but if you're careful, you can see sunspots without a telescope. They're big enough to see. So this is the Sunspot Record, basically just counting the number of sunspots on the sun ever since people started doing it regularly, back in 1600. So first thing to notice is there's a semi-regular cycle. About every 11 years, we have a minimum and a maximum of sunspot numbers. Right now, we're about at solar minimum. So I didn't show you a picture of the sun today, which I might do other years. But that's because the sun today is really boring. There's actually been no sunspots for one of the longest stretches of time ever recorded, except for back in 16-something or other, which we'll come to in a minute. So right now, we're at solar minimum. However, every 11 years, you can have a peak where there's a large number of sunspots, several hundred on the sun. But you can see that this cycle is not constant. Right? It's not a nice sinusoidal oscillation. The amplitude goes up and down, the period changes, and back here, 1650 to 1700, there's no recorded sunspots there because people weren't looking. They had telescopes, they looked at the sun, but they didn't see any sunspots. So it is, we know, possible for the sun to have no sunspots on it for an extended period of time. This is called the Maunder minimum and coincided with what's sometimes called a mini ice age in Europe. So the UV output of the sun is correlated with the number of sunspots, and that affects weather and climate. And this is another reason why we can probably say that the sun isn't impacting climate change as much as people are. Since about 1950, solar activity has basically been declining. So if anything, we'd expect the Earth to be cooling if it was down to the sun. Okay, so that's sunspots and solar activity, but so what? Who cares? Dark spots on the sun don't bother us, right? The problem is, sunspots cause solar flares. So look in the middle here. This very intense brightening and reconfiguration of the magnetic field is called a solar flare. So this video shows, here's another sort of zoom in on the same bit. You can see the intensification of the light around the sunspots in the magnetic field. So what's happening here is those intense magnetic fields that stick up out of the sunspots are pointing in opposite directions. And if they're pointing in opposite directions and they get pushed together, something called magnetic reconnection can occur. And effectively, magnetic field lines are like elastic bands. And when they reconnect, you release the energy in them. So those magnetic field lines in the sunspot are reconnecting with the one next door. The energy in the magnetic field is being released, and the magnetic field lines are pinging back towards the sun like an elastic band and shooting all that hot plasma that was contained in them onto the sun. And when that happens, those particles can get very, very energetic. So we're talking near fractions of the speed of light. And that, when they hit the surface of the sun, they then release X-rays, gamma rays, UV light, and as it cools down, UV light, and infrared. When these happen, in the UV part and X-ray part of the spectrum, they are brighter than the rest of the sun. So very extreme solar flares cause massive X-ray doses, which obviously come and hit the Earth. So if you're on the sunlit side of the Earth, on the ground, you wouldn't notice anything. The atmosphere blocks them all. But if you're a satellite, or if you're high up in the atmosphere on an aeroplane, then the impact is slightly different. Nothing dangerous, but we need to consider it. Solar flares were discovered in about 1859 from the ground with visible light observations, but only really observed in space and understood more fully in the space age. And so in the space age, actually, we owe a lot to nuclear weapons monitoring. So one of the first uses of space was governments putting up satellites to monitor radiation to see if anyone was exploding nuclear weapons. And what they detected was a lot of X-rays, but they're all coming from the sun. So we actually have an X-ray intensity time series going back to the 60s. And from that time series, we have made a set of scales, or scientists have made a set of scales. So A, B, and C, it's a logarithmic scale. So if you have 1 to 9, you've got an A, 10 to 90, it's a B, 100 to 900, it's a C. And, A, B, and C, great. They thought that was probably the end, 3 decades, 1,000 times the base level, that's great. But then bigger flares started happening. Okay, these are really huge, we'll call them M for, massive or something. Wait a bit longer. There's even bigger flares. Okay, this is definitely it. We're going to call this top of the scale, right? X. X for extreme. The largest flare ever seen is something like X40. So what that really means is we need another letter beyond X, right, to categorize the very largest flares. But the scientific community has kind of got bored with letters, and they're just going to stick to X-ray flux from now on. So what you will hear in a space weather forecast, and what you may want to measure if you're going to run a space weather forecast, is intensity of X-rays, and that's classed on this scale A through X, which is 5 orders of magnitude in terms of X-ray flux. Okay, so that's solar flares, explosions on the sun that produce radiation. Now let's look at what's coming off the sun in terms of solar wind and CMEs. So when one of those solar flares occurs, half the plasma, or maybe a bit more or a bit less, will be shot down towards the sun to cause the flare. Whatever was above gets pinged out by the magnetic field that was above it and shot into space. So the way you measure that is with something called a coronagraph. So here is a coronagraph. The sun is in the middle, and it's about the size of this white circle, but a disk has been stuck in front of the sun to block it out. That means your camera sees the light reflected from the plasma that's otherwise around the sun. So this was a very active period in 2003 called the Halloween storms, and you can see every couple of hours there's a CME, one of these big explosions, coronal mass ejection, big explosion of plasma. And they shoot off both sides of the sun all the time, and they are faster than the surrounding solar wind. So if you think, sort of up here at the north and the south pole of the sun, and maybe out the side here when there's not a CME, you have something called the solar wind, which is the background plasma that just fills the solar system, and that travels between 300 and 700 kilometers per second. These CMEs, when they shoot out, some of them are the same speed as the solar wind, but they can be up, as fast as up to 2,500 kilometers per second. So they're 2 or 3 times faster than the solar wind. They carry a lot more density than the solar wind does, so they're a bigger push against the Earth. And we can see another effect of CMEs here as well in these white speckles. So you may have seen a couple of seconds ago the screen kind of whited out with the snowstorm. So when these CMEs are very fast, they actually have a shock wave in front of them. They're going supersonic through the solar wind. That shock wave takes the plasma in the solar wind and accelerates it up to a fraction of the speed of light. So the white kind of snow that you saw on the screen there is actually radiation, intense alpha particles and protons of mega electron volts to giga electron volts in energy hitting the camera. So this is the second big hazard of space weather after X-rays from flares, is radiation in terms of particles, electrons, protons and alphas, coming from the shock waves of CMEs that travel outwards. So inside a CME, here's a cartoon. Here's one of those nice CMEs exploding off the sun, and it has this characteristic kind of light bulb shape because of the magnetic field that's inside it. So you had the magnetic field coming up out of the sunspots into a loop. That loop, the top got pinched off and shot into space. So you have this kind of what's called a flux rope. So it's kind of a coiled rope-like structure of magnetic fields through this blob of plasma that's shot off. So that's why you have a sort of semicircular or circular shape. And the intense patch in the middle is the plasma that was trapped in that magnetic field when it was part of the corona. So here is a cartoon of a CME when it's reaching the Earth. There's the Earth. So you can see these tangled up, coiled up magnetic fields forming the magnetic cloud. And this CME is traveling out, a few thousand kilometers per second. So radiation is one of the big risks posed by space weather. And as we said, part of that's from the solar flare, part of that's from the CME. And those two things have different signatures when you look at the radiation. Flares cause radiation events called impulsive events, and CMEs cause radiation events called gradual events. And those names, you could probably guess where they came from. It's just from what they look like when you're measuring the radiation. So here is energetic protons measured by spacecraft in Earth orbit. This is a solar flare. You get a sudden impulse that dies away fairly rapidly in terms of radiation. This is a gradual event caused by a shock wave. So you can see several days before the shock arrives, the radiation gradually increases. It's a logarithmic scale, so although it looks kind of abrupt, it's actually a fairly gradual increase. And then it peaks where the shock of the CME gets to the Earth and then dies down again. So again, no risk to you if you're on the ground, but if you're a satellite, this is a big issue.